All right, YouTube, I asked you to post your physics questions online, and right out of the gate, I got a question that I absolutely love. The question goes like this. We take 512 identical mercury drops. We're going to pretend this ball is a drop of mercury. And we charge each of those drops of mercury to 2 volts. Now, if we were to combine 512 of those drops, I'll turn these up right, because somebody's going to light me up in the comments for that. There we go. Okay. If we were to combine all those drops, what would the total voltage of that drop be? Now, one of the reasons I absolutely love this problem is because when people first look at the problem, their first instinct and their first thought is almost always absolutely wrong. You see, when people see the word voltage, they don't think of charge accumulated on the outside edge of a ball. What they think of is a battery. And if you were to take 512 batteries, which I don't have, I've got 3 of them. If you were to take and combine batteries like this end to end, you're simply adding up their voltages. And so people think, hey, if we're going to have 512 little 2-volt charges and we start putting them together, shouldn't we just be adding up all of their voltages? But that's just flat out wrong. And it comes from not understanding really what's going on with the charges in this problem. So let me show you a little bit closer what's actually happening.
See, what the textbook writers who wrote this problem expect you to know is that the charge is evenly distributed along the shell of this drop of mercury. And the voltage is measured relative to a point a long ways away from the droplet. See, the short answer in this question is that we're simply applying the equation. Voltage is equal to KQ over R.
But here's the cool part. To get a better understanding of what's happening with these charges, let's look at a version of this problem that you probably have much more experience with that you can look at in a much more intuitive way.
See, rather than assembling 512 charged particles in search of a change in voltage, let's assemble 512 masses in search of a change in gravity. See, let's say this is an asteroid with some mass m and radius r, and on the surface of that asteroid there's an acceleration due to gravity of 1 meter per second squared. Imagine we took and combined a whole bunch of these asteroids together into a little planet. Well, I want to figure out what that acceleration due to gravity would be on the surface of the planet. Now we know the acceleration due to gravity is given by gm over r squared. And that relationship between the acceleration due to gravity and mass is very similar to what we see over here with our relationship between voltage and charge. Now granted, this acceleration due to gravity is proportional to 1 over r squared instead of 1 over r, and I'll talk more about that in a little bit. But applying this equation to this situation, we can see that for a single mass, 1 meter per second squared is equal to g, the gravitational constant, times the mass, divided by, I'm going to call this capital R, that is the radius of our little asteroid, and that's squared. Now this is for a single mass, so I'm just going to say m sub 1 and r sub 1. But if we were to combine 512 of these masses, we're looking for that acceleration due to gravity on the surface of that mass. So using this same equation, we're going to have g times our combined mass over our total radius squared. Now the combined mass is easy to work out. By putting together 512 of these masses, the total mass is just going to be 512 multiplied by our initial mass, or the mass of a single particle. And we can say the same thing about the combined volume of our little asteroids. The volume of all of our masses is going to be 512 times the volume of a single mass. But remember, this equation isn't based on volume, it's based on radius. But you remember, volume is given by 4/3 pi r cubed. So applying this equation to each side of our little volume equation here, we have 4/3 pi times the radius of our combined masses cubed, and that's going to be equal to 512 times 4/3 pi times our initial radius cubed. Now you'll see this 4/3 pi cancels out, and that leaves us with the radius of all of our little masses combined is 8 times the radius of our single mass. So now taking our relationship for our mass and our radius and plugging them into this equation right here, we get the gravitational acceleration that we're trying to solve for is equal to g times 512, our initial mass, divided by 8 times our initial radius squared. And if I rearrange this, You'll see this function right here is the same as what we started with up here. This is equal to 1 meter per second squared. Sure, we didn't know the mass or radius of our little asteroid here, but we knew the acceleration on the surface was 1. So I can just plug that in right here. And this leaves us with our acceleration due to gravity that we're solving for is 8 meters per second squared. Now going back to our charges, things work almost exactly the same way here, except there's one key difference. See, with our planet, we solve for an increase in the gravitational acceleration, or really, the gravitational field, which is the mechanical cousin of electric field, not electric potential or voltage. Voltage is more like gravitational potential, so the equation we're going to use over here is proportional to 1 over r rather than proportional to 1 over r squared. But other than that difference, we're going to go through almost the same exact process as what we saw over here. First, looking at a single drop. We know a single drop had a total voltage of 2 volts. Now those 2 volts are the result of some amount of charge, and I don't know the total charge. We're just going to call it Q, which is accumulated on the outside of this shell, which has some total radius, which we don't know. We're just going to call it R. So combining 512 of these drops, we're solving for the total voltage that is the result of some combined charge, which is acting on the edge of some large sphere. Now, just like our masses combined over here, we're going to have 512 of these charges, which are going to combine over here. So we can say our total charge is 512 times a single charge. And when these drops of mercury, we're going to see their size change exactly like what we saw over here. The volume of our combined drops is going to be 512 times the volume of an individual drop. But just like over here, solving for the radius, we find our combined radius is 8 times the initial radius. So again, taking these two equations and combining them into our equation for the voltage, we get this expression. And knowing that this term right here, kq over r, is exactly what we started with for a single drop, we're really saying that this term right here is equal to 2 volts. We can say that our total voltage that we're solving for is 128 volts. Now, both versions of this problem are almost identical. I mean, they have slightly different equations governing what's happening here, but the process of coming up with a solution is the same in both cases. And they have the same challenge points in them. In this case, it was coming up with the volume. That tends to be where people get lost here. But the point is, if you're trying to solve a problem like this, turning it into something that's mechanical, that people understand a little bit more intuitively, can go a long ways.
And this is a point I always try to make in my classes. Concepts like electric field and electric potential are concepts that you interact with mathematically, but you don't really interact with them tangibly in the same way that you do, say, gravity on a day-to-day basis. And if we can tie something that we understand, like gravity, back mathematically to something that's a little bit harder to understand, like electric fields or electric potential, then we can reason our way through problems that otherwise would seem pretty complicated. And that brings us up to my absolute favorite part of this problem, and that has to do with work. You see, if we look at each of these as identical charges, the electric force between them is going to actually cause them to push apart. So the only way we're ever going to get these two charges to combine is by pushing on them. And no different than when compressing a spring, we have to push inward and do work on that spring to compress them. And so it's in physically pushing these charges together that we're giving them the voltage or the electric potential that we're actually trying to calculate in this problem. You see, even though this is an electrostatics problem, we can get at what's happening here just by looking at this mechanically. We have to do mechanical work on these charges in order to get them to combine. And that's probably one of the coolest things about this problem. So YouTube, thanks for this question. I absolutely enjoyed going through it with you. If you have any more questions, just drop them in the comments below. I'm happy to answer your questions or your problems. And on that note, that's all for now.